So these are some model problems present in this topic. If there's any doubt, let me know. So next topic, geometry. So geometry is one of the vast topics present here. So when compared to other topics, this is the topic where we are going to discuss a maximum number of concepts like circles, triangles, quadrilaterals, and also general geometrical concepts and related to those 3D figures like cube, cone, cylinder, sphere, like that. Different concepts are there. So one of the important point where you have to pay attention or where you have to be careful in this topic is when you come across multi-conceptual questions. Multi-conceptual questions. That means to answer a question, you might have to use two or more than two concepts. So in those cases, getting ideas is important. Like what idea to use now, how to proceed further, then what concept to pick up, then what idea to use, like that. Because I said there are a lot of concepts here. Out of all those concepts which we learn, getting those ideas, like what ideas we have to employ here, that's important. So whenever you come across multi-conceptual questions, pay attention to that model. Like what he is asking here, based on this information, what concepts are we using? So when you come across similar model questions, you must be able to employ those ideas. And one more important point which you have to keep in mind while solving these problems in geometry is don't go by the looks of the figure. Don't go by the looks of the figure. The looks of the figure means here figures are not drawn to scale. As figure is not drawn to scale, you cannot just simply go by the looks of that figure. So if some information is given in the question, use it. If some information is provided in the figure, use it. But do not make any assumptions. Do not go by the looks of the figure or do not make any assumptions. So all we can do is we can only use the information given in the question or in the figure, and through our mathematical reasoning and through our geometrical reasoning, if we can deduct any facts, use them. But don't go by the looks, do not make any assumptions. For example, let's say a triangle is drawn like this. Now this looks like a right angle triangle. This here looks like a right angle triangle. Now just because it looks like a right angle triangle, in the exam, for example, let's say a simple figure like this is given, you cannot consider it as a right angle triangle. All we can say here is ABC is a triangle. For us to consider it as a right angle triangle, he should have given some information in the question. Like one of the angle is 90 degrees. Or in the figure, let's say use this symbol. This is the symbol which uses to denote right angle. In the presence of this symbol, you can say this is a right angle triangle. But in the absence of this or any other information in the question, we can only say that ABC is a triangle. So we cannot go by the looks of the figure. We cannot make any assumptions. For example, let's say there is a line segment AC. B is a point on this line segment AC like this. So here is AB greater or BC greater? AC is a line segment, B is a point on this line segment AC. Is AB greater or BC greater? What about the relation between lengths of AB and BC? So here when you come across these kind of questions, we cannot compare AB and BC. So because if you are saying BC is greater, you would be saying that because it looks greater. But the point which we are discussing here is don't go by the looks of the figure. So when you have a simple line segment like this, AC and B is a point on AC, you cannot compare AB and you cannot compare BC. So one of the important point here is you have to consider this point B as a point which could be anywhere on this line segment AC. This point B could be anywhere on this line segment AC. Because sometimes he will draw some figures like this. He will say this is 10 units, this is 10 units. Now does the two lines look equal? No. But he said 10 10, you have to take it as equal. So as figures are not drawn to scale, do not go by the looks of the figure. So all we can say here is AC is greater than AB. AC is greater than BC. This we can say. Because we don't know where this point B is. It could be anywhere on this line segment AC. But one thing is, it will definitely it will be in between A and C. AC means distance between two end points, the total length of a line segment. So the total length of a line segment will be greater than a part of it because A and C are end points. We don't know where B is, but it is somewhere in between A and C. So the complete length of a line segment AC will be greater than AB or will be greater than BC. So this you can say. But in between AB and BC, we cannot compare. So be careful while dealing with these geometrical figures because in certain models, in some questions, he will draw figures in such a way that we are more tended towards making some assumptions or going by the looks. And if we end up doing that, again, we will arrive at wrong answers. So only use information what is given to you. Do not make any assumptions. So in this topic, going through formula sheet, we will look at the different concepts involved. I think page 156 or something like around there. Can someone tell me this page number? Once in it will be in between 155 or 160 like that. Formula sheet on geometry. Questions from 45. What's that page number? $158. So look in this page 158 to try these questions from 45 to 55. So most of them are concepts. Only one or two problems are there. So if you know that concept, fill that, or else you go to the next one. We will discuss them in 10 minutes. Concentrate here now. Let's look at these concepts. First, length of the arc of a circle. An arc. An arc is a part on the circumference of a circle joining any 2 points. An arc is a part on the circumference of a circle joining any 2 points. So let's say there is an arc AB. If it makes an angle theta at the center, then length of this arc is theta into 2 pi r by 360. So length of the arc of a circle is theta into 2 pi r by 360, where theta is the angle it subtends at the center. So length of the arc of a circle is theta into 2 pi r by 360, where theta is the angle this arc subtends at the center. If you look at how we are getting this formula, for example, let's say we are initially at point A. If the rotation is for 360 degrees, total angle around a point is 360. If the rotation is for 360 degrees, you will start at A, cover the entire circumference of the circle, and we'll end back at A. So if rotation is for 360 degrees, length covered is the total circumference of the circle, which is 2 pi r. If it is 1 degree, we say 2 pi r by 360. So length of the arc of a circle is theta into 2 pi r by 360. Similarly, area of sector. Area of sector is a theta into pi r square by 360. Area of the sector of a circle is a theta into pi r square by 360. So sector area means it's the area covered between arc and radii of the circle. So area covered between arc and radius of the circle, we call it sector area, this particular area. So if this sector subtends an angle theta at the center, then area of this sector is a theta into pi r square by 360. Now we get this using similar kind of reasonings. For example, let's say we are initially at point A. If the rotation is for 360 degrees, we will cover the entire area of the circle and we'll end back at A. So let's say we are starting from A. Total angle around a point is 360. If the rotation is for 360 degrees, total area of circle will be covered, which is pi r square. If it is 1 degree, we say pi r square by 360. And for theta degrees, it is theta into pi r square by 360, using those unitary relations. So length of the arc of a circle is theta into 2 pi r by 360. And area of the sector of a circle is theta into pi r square by 360. So it can't be what is arc. Arc means it must be a part on the circumference of a circle. Similarly, sector. Sector area is the area covered between arc and radius of the circle. So radius. Radius means it will be equal to radius because that's what we call a sector. This particular area, OAB, that we call it sector. Next one. Next, we have an important property related to cyclic quadrilaterals. If all the four vertices of a quadrilateral lies on the circumference of a circle, if all the four vertices lies on the circumference of a circle, we call it cyclic quadrilateral. So if you observe here, A, B, C, D, all four vertices are lying on the circumference of a circle. Or in other words, if you can draw a circle passing through all four vertices, we call it cyclic quadrilateral. And regarding cyclic quadrilaterals, one of the important idea is sum of opposite angles in a cyclic quadrilateral is 180. Sum of opposite angles in a cyclic quadrilateral is 180. 1 and 3 opposite. So angle 1 plus angle 3 is 180 degrees. 2 and 4 opposite. So angle 2 plus angle 4 is also 180 degrees. Sum of opposite angles in a cyclic quadrilateral is 180 degrees. So angle 1 plus angle 3 it is 180. Similarly, angle 2 plus angle 4 is also 180. So when some angles are given, you have to find out some other missing angles. There will be employing those. Next one. Now, if it's a curved part on the circumference of a circle joining any 2 points, we call it arc. This particular area, this particular length, AB, we call it arc. If it is a line segment, joining any 2 points on the circumference of a circle, we call it chord. If it's a line segment joining any 2 points on the circumference of a circle, we call it chord. So if this arc AB or chord AB subtends an angle theta at the center, angle it subtends in the remaining part of the circle is theta by 2. If an arc or a chord makes an angle theta at the center, angle it subtends in the remaining part of the circle. Remaining part of the circle is theta by 2. Half of what it makes at the center. Half of what it makes at the center. And also if you look at the terminology which I am using, I said if an arc subtends an angle theta at the center, angle it subtends in the remaining part of the circle. Remaining part. So if you are considering this arc AB, for this arc AB, remaining part is anywhere here. So take anywhere here, angle it makes is theta by 2. Somewhere here also it is theta by 2. Half of what it subtends at the center. So that question there in formula sheet is application of this. He took 2 points on the circumference of a circle. He has given what is the angle they subtend at the center. You need what is the angle they subtend at the remaining part of the circle. Let's say this is A, this point B here, C here. If this arc BC or chord BC subtends an angle theta at the center, angle it subtends in the remaining part of the circle is theta by 2. So from which we say angle O. Sorry, angle A is angle O by 2, which is 132 by 2. We get it as 66 degrees. So if an arc subtends an angle theta at the center, angle it subtends in the remaining part. Remaining part of the circle is theta by 2. Half of what it makes at the center. Next one is application of this concept. So he's asking angle in a semicircle. If you draw a diameter in a circle, when you draw a diameter, it will divide the circle into 2 equal parts. When we draw this diameter, it will divide the circle into 2 equal parts. Each part we call it semicircle. So each part we call it semicircle. And this diameter is nothing but line segment joining any 2 points on the circumference of a circle and passing through the center. So angle this arc AB or chord AB makes at the center is 180.